Hello everyone. Thanks for coming today. So it's my pleasure to introduce Marica Minucci. So Marica is a final year PhD student in Queen Mary University of London, and she's working on the supervision of Juan Antonio Valiente Cron. Before starting her PhD, Marica completed a master's degree in theoretical and mathematical physics at the University of Naples, Federico II, with a thesis entitled Hyperbolic Equations and General Relativity, under the supervision of Giampiero Esposito. And well, she is a visitor of CENTRA, and she will be here for about 2 months. So if you want to know more about cosmological spacetimes and conformal methods, she is in the 4th floor in Masato's and my office. So you can ask her more about this stuff. I have 2 months to ask her. So without further ado, Marica, the stage is all yours.
So first of all, I would like to thank the organizer for giving me the opportunity to present my work today. Let me just minimize this. Okay. So today's talk is based on this paper, which is of course a joint work with my supervisor. In this paper, what we do is to make the first step in trying to use a technique based on conformal methods to study the nonlinear stability of the Schwarzschild-de Sitter spacetime, in particular the cosmological region. But before diving into this subject, what I would like to do is to give a little bit of history of conformal methods in general relativity. So the use of conformal methods in general relativity goes back to a seminal idea of Penrose. They had this idea of studying the large-scale behavior of gravitational fields by using an operation of conformal rescaling. In this idea, we have the physical spacetime, which you can think of it as the solution to the asymptotic equation, is conformally mapped into a physical spacetime via the relation of conformal rescaling. In this way, we have that the physical manifold tilde is conformal to the interior of the physical manifold, and points that used to belong to the infinity in the physical manifold are mapped to a finite position in the physical space. We denote the conformal boundary, so it's characterized by the vanishing of the conformal factor. Now, since the physical metric contains the same causal information of the physical one might wonder what is the relation between the conformal structure of the space-time and the asymptotic equations. So in particular, one might want to know how does the asymptotic equation behave under the conformal transformation of the matrix? The answer is not very well. Since this conformal transformation defines isometry classes of solutions, then of course the resulting equation would not be conformally covariant. And one can see this by having a look at the transformation law of the Ricci tensor. So R tilde would be the physical one, R is the unphysical one. So if one replaces R tilde, the Einstein vacuum asymptotic equation, and assume that the conformal factor phi is a function of the solution manifold, one has an equation for the matrix G that has 2 problems. The first one is the presence of factor that behaves like 1 over chi. So this means that if you want to use this equation to study the behavior of the solution x chi, you have a system of singular equations. And the second problem is that both the conformal factor and the unphysical manifold are not known a priori. They are in fact a function of they really depend on the geometry of the solution, and so they need to determine along with the metric G. But the task of formulating a conformal version of the asymptotic equation is not impossible. In fact, the first formulation of this equation, known as the regular conformal asymptotic equation, have been formulated by several authors. What I would like to do here is to introduce not the first version, but the frame version. So this means that all the tensorial quantity that appears in this equation have been decomposed in terms of a G orthonormal frame. So that then a regular set of equations can be prescribed once we define many zero quantities here, and the full set of equations is the following. So at this point, in this equation, we have the metric somehow is hidden underneath all these decomposition. And one might wonder how to study this equation, to use this equation to somehow solve some specific problems. So if you want to study the solution to this equation, what one needs to do, in particular, if you want to study the evolution of the system, one needs to, first of all, construct a suitable system of evolution equation. And this can be done by performing a procedure that is called hyperbolic reduction procedure that mostly concerns fixing the gauge. With this set of equation, gauge fixing means introducing some gauge source function so that then you have suitable evolution equation. The other thing one needs to do if you want to study the behavior, the evolution of this equation, to study the behavior of the solution, one needs to know what is the value of the solution on a suitable initial surface. And then this would be the Cauchy problem, right? Or in general, initial value problem. Now, there is a full literature of work based on solving or treating the Cauchy problem or the initial value problem in general relativity. Here, what I'm focusing on is the first result made by using conformal methods, which is due to Friedrich, and it's contained in this paper and is related to the nonlinear stability of the Minkowski spacetime. But at the same time, there is another one that is related to the nonlinear stability of the De Sitter spacetime, which is contained in this paper. Now, how this whole thing relates to what we're doing today. So today, what we're doing is to try to start to use these methods to address the stability of a black hole type of spacetime. Still a cosmological spacetime, but in which once we have some form of black holes appearing. What we do, instead of using this form of the equation, we use a more generalized version of this equation, so that once we have to perform the gauge fixing operation, instead of having to use the gauge source function, what we use is a gauge that it can be fixed by using the property of some conformal curves that you can formulate in this spacetime. So what is the strategy then? So these conformal curves are called conformal geodesics. So for people who are not familiar with conformal geodesics, this is a pair of a curve and a covector that satisfy the conformal geodesic equation. Now, these curves are conformally invariant curves. And the reason why we're interested in them is, first of all, this property. So if we prescribe this curve to be time-like, and we give this, we prescribe this conformal rescaling relation and this normalization condition, one can use the conformal geodesics as long as along with the Einstein equation to get an ordinary ODE for the conformal factor. So this means that then if we prescribe when we use this constraint and we prescribe this initial data, one can in principle use the conformal geodesics to solve this ODE for the conformal factor and obtain a conformal factor out of the conformal class. So you can use the conformal geodesic to single out an unphysical metric out of the conformal class. The other reason why we are interested in these curves is that they can be paired with a Weyl connection. So a Weyl connection is an unusual connection, which is torsion-free, but it's non-metric. And the relation to define the Weyl connection is the following, where F is a fixed vector, and then from now on, every time you see a hat symbol, it will just mean that it's a quantity that is written in terms of this connection. Now, with a Weyl connection, it comes a Weyl propagation equation. So if you want to propagate a frame of some coordinates along the conformal geodesics, you need to have a suitable propagation equation. And this propagation equation is provided by the following equation. So this equation will be useful in the following. Now, from now on, I need to introduce some quantities that will be useful once we define the main evolution system. The first one will be this C quantity. There is a convenient quantity because it contains both information about the covector that defines the Weyl connection and the conformal factor of theta. Then, since, as I said, all the quantities we have are related to Weyl connection, one has that you can introduce the decomposition of the Riemann tensor in terms of the Schütten tensor and the Weyl tensor. And then for our use, what we do, instead of using this formulation of the Weyl tensor, we introduce the scale Weyl tensor via the conformal transformation of this form. So then give us this recipe. What we do by using this conformal geodesic and these wide connections, to construct this conformal Gaussian gauge system. This system generalized the standard Gaussian gauge system, and they are made as follows. So you have an initial hypersurface. On this region, on this hypersurface, you select the region U, and you cover it with a non-intersecting congruence of conformal geodesics. Then, as I explained before, you can use the property of the conformal geodesic to single out an physical matrix out of the conformal structure of the spacetime. Then what we do is to construct a G orthogonal frame by prescribing the time leg or the time derivative of X. And then one can pair the conformal geodesics to the wide connection by fixing the covector defined the wide connection being equal to the covector defined in conformal geodesics. At this point, this frame will be bi-propagated along the conformal geodesics. Then, to complete the system, we have to choose a time parameter tau in conformal geodesics to be also equal to the time length. Then, given this, what we're left to do is to, on this initial hypersurface here, to prescribe some local coordinates. Now, since we want to have coordinates that we can propagate along the conformal geodesics, we need to make sure that we can extend this coordinate out of the initial hypersurface. So what we do is to ask the conformal geodesic that intersect this hypersurface intersected only at one point without intersecting each other. And then this coordinate x alpha will be considered as constant along the geodesic. So along the prescribed geodesic, only tau will change. And so the full set of the conformal factor, the bi-propagated frame, and this coordinate is known as conformal Gaussian gauge system. So now the second ingredient is given by a more general version of the asymptotic equation, of the conformal asymptotic equation. So now they look quite unfamiliar. So if you want to have some intuition of where they come from, you can think of them as equation that you obtain once you have your conformal asymptotic equation in a frame formulation, and then you change connection. So these are the conformal asymptotic equation that you have once you pass from the Levi-Civita connection to the Weyl connection. Now, in terms of some extra zero quantities and use of geometric and algebraic part of the Riemann tensor, one can formulate this equation in this form. Now, since this equation don't explicitly involve either the conformal factor or the t, these are determined aside from this equation by the procedure that I just described. Now, to relate a solution to this equation, to the solution to the vacuum asymptotic equation, one needs to prescribe some extra zero quantities. And so the supplementary conditions are involved in the so-called propagation of the constraints and play a role when you want to formulate the solution that you have to this equation in a solution to the initial vacuum asymptotic equations. And then we need a set of constraint equation. In this case, this is a set of conditions that is prescribed on a three-dimensional space-like hypersurface, in this case by the standard conformal asymptotic equation. And this is expressed in terms of a frame of which this is the first component. The idea is that you can use this equation to be solved on an initial hypersurface and then to recast eventually the solution to the partial solution, the partial solution to a solution to the vacuum asymptotic equation. Now, I said so many things, but what about the Schwarzschild-de Sitter spacetime? So the Schwarzschild-de Sitter spacetime is a spherically symmetric solution to the asymptotic equation with positive cosmological constant. The null element in the standard Schwarzschild-de Sitter coordinate is the following, where T is a function that contains both information about the mass of the black hole and the cosmological constant. Now, by introducing a conformal rescaling, one can rescale this line element so that now can be recasted as follows, where capital M contains both information about the mass of the black hole and the cosmological constant. In terms of the structure of the spacetime, since the mass is bounded between the following values, and we are in the case of a positive cosmological constant, one can factorize in the following way. where RB, RC are positive root, and R minus is a negative one. One can explicitly write down these roots by using Cardano's formula for cubic equation and define this quantity phi. The reason why we do this is that in this way we have a control about what's happening. What I mean, what's happening is that there are three possible situations that can happen in this case. So there is the case in which the space-time is called sub-extremal. That is the case that we're going to investigate, in which they somehow joins the futures of the black hole and the cosmological space. There is the extremal case, where we have only one horizon, a killing horizon, and the upper extremal case when there are no horizons. So what we're going to do is then to consider value of the M of phi so that we are in the sub-extremal case, and we can consider the system as a black hole in a cosmological setting. And why I say this is because if you look at the Penrose diagram of this space-time, you have that this is a periodic space-time. So we can just limit to this unit here. We have the cosmological part, so cosmological horizon, conformal boundary. The black hole part, so black hole horizon, black hole singularity. And we have this interesting point Q and Q prime, where the horizons and conformal boundary plus black hole singularity meet. Now, when wanting to apply this strategy to study the nonlinear stability of the space-time, what we had to do is to study how the conformal geodesics behave in the whole space-time. So the idea would have been to take an initial hypersurface passing through this point called the bifurcation sphere corresponding to t equal to 0, and then see what happens. So if this conformal geodesic behave that's enough, one can in principle use them to evolve the solution and then have the nonlinear stability of the whole space-time. But what happens is that previous analysis on the geodesics contained in this paper shows that as you get closer to Q and Q prime, you see that the geodesics start to accumulate. The other problem in controlling is not only controlling the evolution, but it's also the fact that Q and Q prime contain singularity of the conformal structure. So our technique as it is cannot be directly used to prove a statement that contains this point. So what we decided to do is to say, okay, we can just focus on the cosmological part, so one of these two sides, and then consider an initial hypersurface corresponding to R equal to constant in the cosmological part of the spacetime. Now, since this technique doesn't really depend on a specific initial hypersurface, one is a whole collection of hypersurface which are in purple here with R equal to constant. So what we do is to select one of these hypersurface with R equal to constant, and then study the behavior of the geodesics first. So let's say that we take this one. So since we want geodesics that leave this hypersurface orthogonally, this means that in our calculation, since beta squared is equal to 0, the resulting congruence of conformal geodesic turns out to be the standard matrix geodesic. Then what we do is to prescribe to use this conformal geodesics to find a natural conformal factor. So we select this initial data on this initial hypersurface, and then we get this conformal factor. Now, we have two values of tau because this problem is really symmetric to study the problem on this other part of the space-time. So tau plus equal to 2 corresponds to the position of psi plus. Psi minus equal to -2 corresponds to psi minus. But we are just analyzing this part. Now, when study the behavior of the geodesics, since, as I said, we want to exclude this point, what we need to do is to perform a surgery on our initial hypersurface, and then to cut it in correspondence to two values of the time, minus t bullet and t bullet. So then now I will, from now on, this part of the hypersurface, R bullet, as being the one contained in between minus t bullet and t bullet. And then what about t bullet? So t bullet needs to be chosen in a way that the future domain of dependence of R bullet has a non-empty intersection with the conformal boundary. So we want that then our strategy allows to say something about the conformal boundary. So this key bullet cannot be too far down because otherwise our evolution would not contain any portion of sky. Now, by studying the behavior of the geodesics and also using Mathematica to double check our analytical calculation, we found out that this conformal geodesic not only reach the conformal boundary, but also they don't develop any caustics. So you can use a singular geodesics to transport to evolve your system. And then this is summarized by proposition 1 that says that the congruence of conformal geodesics given by the initial condition leaves the initial hypersurface S star and reach the conformal boundary star plus without developing any caustics. So we have a system of conformal geodesics that behave nice enough to perform, to use our strategy. Now, the next thing in our recipe is to construct a system of conformal Gaussian coordinates. So to do that, we can define sDS tilde as the original region in the physical space that we are analyzing. And then this is mapped conformally to this new region here that you can somehow see in this picture in terms of the coordinates PNR instead of T and Z. Now, because of how nicely this conformal geodesic behave, this geodesic define a map between the standard Schwarzschild-de Sitter coordinates and a new set of coordinates. Since these geodesics don't intersect, this map is not only analytic, but it's also invertible. And because of the inverse map is also well defined, that we have a transformation between the standard Schwarzschild-de Sitter coordinates into the conformal Gaussian coordinates. And so in general, we have proposition 2, where this congruence of conformal geodesics induces a conformal Gaussian system of coordinates over the whole domain of dependence of our bullet, which is related to the standard Schwarzschild-de Sitter coordinates by a map which is analytic. So now we have the conformal factor, we have a system of coordinates. Now what we'd like to do is to recast the Schwarzschild-de Sitter solution in conformal Gaussian coordinates as a solution to the extended equation. And to do that, we need to introduce a bi-propagative frame. So in this case, since the conformal geodesics satisfy this condition, then the bi-propagation equation becomes just the standard propagation equation that you have for a Levy-Chilida connection. And then we can construct the frame by fixing the time lag of the frame equal to x bullet, then we have a relation to derivatives, so that this is the first component of the frame. One can also fix the radial lag by introducing omega in this way, so that the scalar product between x to the prime and omega is equal to 0, and the radial radial lag is this one. And one can also check that this component can really be bi-propagated by using this relation. Now, for the other two components, E2 and E3, one chooses them in this way because one wants them to span the tangent space to the two spheres that are associated to the orbits of spherical symmetry. In this particular case, one can show that if you give E2, E3 on an initial hypersurface, one can map these coordinates to a set of coordinates E2 and E3 on the conformal manifold that we are considering by asking that the original, by extending A to A and A to A star, so the one that you prescribe on the initial hypersurface, along the conformal geodesic. So you transport them along the conformal geodesic. And so one has also in this case another proposition that somehow summarized that we can construct a frame which is also bi-propagated, and then this frame also depends on the physical appropriate time and the initial position of the curve star. So we're almost done, but we made a simplification in this case that somehow is an obstruction to use the theorem that we want to use to prove existence and stability result. what we've done is to define our bullet so that it has topology of an interval times the two sphere. So this will mean that the resulting space-time is the same topology. And so because of this, and we want to use a perturbative approach that needs a solution having compact spatial section, what we need to do is to rephrase our solution with an open interval as a solution, to recast the solution as a solution with compact spatial section. So what we do is a little bit of playing around with the geometry, but more precisely what we do is to consider a Killing vector in the cosmological region, and this Killing vector turns out to be spacelike. Then one can consider an upper surface with Z equal to constant, and this upper surface will have translational invariance. In particular, both the intrinsic metric and the extrinsic curvature will also have this property. Then what we do is to notice that the congruence of conformal geodesics is such that T is constant along a given curve. So the red lines that you see before are all conformal geodesic with constant time. So then one can consider two time-like upper surface, 1 and 2, that are future-oriented time-like geodesics for T equal to minus T bullet and 2T bullet. And use this upper surface to identify a new space-time manifold M bullet bar that corresponds to this region. So the task is then to recast the original solution, a solution for this region here. So how do you do this? So the original metric on this region induces a metric on this whole region here. And then how it does it, so we can consider the conformal geodesic again. So we have the initial data that gave rise to these conformal geodesics are a translational invariant. This conformal geodesic also will have this property. And then the induced conformal geodesics on this whole region will also have this property here. And so given a matrix that is induced in this region here, and given the given conformal geodesics, one can then translate the solution to the extended conformalized field equation as a solution on this whole space-time manifold M bar for it. And from now on, I will refer as the overall solution as U ring. So this will be my background solution. Having said so, to evolve the system and then solve the Cauchy problem, we need some suitable set of initial data. So at this point, one can show that given the constraint equation, one can solve the constraint equation. And from that, from the solution, one can construct algebraically a solution to initial data for the evolution equation. To do this, one assumes that there's a family of initial data set for the vacuum mass field equation that corresponds to perturbation of the initial data set for the Schwarzschild-de Sitter solution on hypersurface of constant R on the cosmological region. So one consider initial data on the hypersurface and then construct the initial data for the evolution equation starting from this initial data. Then one consider U ring star is the exact Schwarzschild-de Sitter initial data. We have an initial data set in red on this region here, which is a small perturbation of U ring. So we have, this is the exact initial data, this is a small perturbation. And our definition of small means small in terms of Sobolev norm. So once we have this, we can use a cutoff function so that the perturbed initial data of an argument can be met by vanishing data on this region here with a smooth transition region. So what we are doing is to, since we don't want to have a solution in the solved part, we just want to have a solution here, we construct the initial data so that they give a vanishing solution here, and then a non-vanishing solution in the part of space-time where we actually want to prove existence and stability. And so this is done by using this cutoff function. And so, yes, so this is what someone just said. Now, one can summarize the whole system of evolution equation by this model system of equation. So one can prove that the main evolution system is both the subsidiary evolution system are of this form. So this means that the use of the extended Einstein field equation, conformal Einstein field equation in this conformal Gaussian gauge can its conformal Gaussian coordinates allow to formulate the evolution equation as a set of transport equation. In particular, if one introduces this perturbative argument where, let's say, you ring with the exact Schwarzschild-de Sitter solution and you bread is a perturbation, one can then rewrite this equation where we know that U ring is the exact solution. So given the initial data, the one obtained by the constraint equation, you know that they actually solve the equation. And so use this procedure to obtain a system of equation for perturbation of this form. Now, because of the matrices, A depends not only on the coordinates, but also on U, and B also depends on U and the coordinates, but is at most quadratic in its dependence. One can show that this is a symmetric hyperbolic system for which one can use Cauchy theorem for symmetric hyperbolic system with compact spatial section to prove existence and stability results. Now, this result needs to be paired with the propagation of the constraint. Yes.
For these transport equations, are there interpretations for the coefficients of the transport equation?
This one?
Yeah.
Okay, so we define B as being, so these are overall quantities. So D and D star are the electric and magnetic part of the scale by tensor. E, gamma, and L are the frame, potential coefficients, and the Schouten tensor. So it's just a way to write down in more compact form instead of having that very unintuitive set of set of equation. And so,
so what is the difference between K and Q? So they're both in front of
okay,
P.
so these are all quantities. So in this case, K just a matrix is with constant. Q is a matrix that depends quantities that they contain quantity depends on the connection coefficients.
Okay.
And again, in this case, is at most linear in the connection coefficients. Then we have these matrices here where they are defined just to, so where there is a dependence, I explicited it, so you will have quantities that are the most quadratic in their dependence. And so because these matrices are positive definite, then you can say that this really is a symmetric hyperbolic system. And since we show that we really have compact spatial section, then we can use Cauchy. Yes. So the idea is that what you can do is to construct patches. So because you have a compact spatial manifold, you can cover this initial hypersurface with you can cover it with patches. I mean, it's compact, so you can cover it up to fill it and then assume that.
But time is also compact here, right?
Yeah.
That's the power of conformal, right? Yeah. So you evolve from tau equals 0 to tau equal 2.
Yeah.
Yeah. So you cannot be very far from this slide.
Actually, you can. So for how this, so ES is also computed. So it corresponds to a specific value of R. So when we computed the background solution, since it's really independent from the slice that you take, we said, okay, but to see if this is really true, we need to see if this background solution really works. If you consider the initial slice as being exactly scribed, right? And then what happens is all the quantities that you can compute behave regularly as scribed, so they don't diverge for value corresponding to scribe. So that's why our final statement would be somehow something contains a little bit more of a scribe because of how everything works. So what we check is also this, that you can really formulate up to scribe, so that the quantity that you can obtain by getting the background solution are really regular, also the conformal boundary. And so, yeah, so one Lakato is local, but you can construct the patches so that then you can identify overlapping solutions. And then since you can do this for every small ball, you can then say that this holds for everything. And then since everything relies on the coordinates, but you can propagate these coordinates, then you can say that it's really independent from the slides that you take. I would say. Any other questions? Okay. So now, propagation of the constraints. So one can prove that also in the case of the propagation of the constraints, in particular of the independent component of the zero quantities that are not involved either in the main evolution system or in the gauge conditions, satisfy symmetric hyperbolic system. In this case, one can actually prove that this system would be a system with initial vanishing condition. And so that also in this case, Cato will give you a result that says that then these zero quantities vanish on this initial upper surface. They will always vanish in the old domain of dependence. And then the main theorem, I will say, is this one, where we say that given this initial data, where U ring is the exact solution with perturbation, then the conformal constraint equation, for the conformal constraint equation, one is that there exists an epsilon greater than zero, so that this perturbed initial data is small and so what known. One has a unique solution to the Cauchy problem for the conformal evolution equation. And then given a sequence of initial data, which is also small, it's Sobolev norm, for the corresponding solution, one has the Sobolev norm goes to zero uniformly in tau as n goes to infinity. Now, we said everything about the extended equation, but we want the solution to the vacuum isofield equation. So by using the propagation of the constraint and the relation between the extended conformal isofield equation and the vacuum isofield equation, we have this corollary that says that given the physical metric, one obtains a solution to which is a solution to the conformal evolution equation. We have a solution to the vacuum isofield equation with positive cosmological constant on M, where M tilde is the future domain of dependence that are folded. And this solution makes a smooth conformal extension with a spacelike conformal boundary. And in particular, the time-lapse geodesics in M tilde can be proved to be complete. And what we're saying here in particular is that there's a region of space-time, M tilde G tilde, which is a nonlinear perturbation of the sub-extremal Schwarzschild-de Sitter space-time, or a portion of the cosmological region of the background solution, which contains a portion of the asymptotic region. And so this is the paper. And now this is a more, I would say, less insightful version of the theorem that I've just showed you before, where we just say, given the initial data, then if the perturbation is small and so known, then we can obtain a solution to the vacuum isofield equation, somehow summarizing what I just presented in the last few slides. So in conclusion, we can use the extended conformal isofield equation and a gauge based on the conformal geodesic to prove existence and stability results for a portion of the cosmological region of the sub-extremal Schwarzschild-de Sitter spacetime. Now, since this is the first step, the next natural step would be to fortify somehow this result by considering a characteristic neutral volume problem on the cosmological horizon, still excluding this point, the prime. And the reason is that we can really take this upper surface to be any constant upper surface, any upper surface with constant R, but you cannot take the cosmological horizon. So our results needs to somehow be away from also the cosmological horizon. But by prescribing a characteristic problem, one can also show that this result really applies also when you are on the cosmological horizon. But still, no asymptotic points. And so what I'm going to do with Edgar is try to address these asymptotic points, because this is conjecture that you can use methods that are more typical in the study of the problem of spatial infinity, like the structure of the cylinder, a spatial infinity by Friedrich. Then one can use to somehow control this region Q prime, maybe have a similar structure as a cylinder for this point, and then eventually using the trumpet upper surfaces by Baumgarten et al. To try to have an existence and stability result for more than the cosmological region, or at least the cosmological region, including the asymptotic. That's it.
Very good. So we have plenty of time. So are there any questions?
I have a like last round you showed the last diagram.
Mm-hmm.
You know, before going to the characteristic problem, can you sort of make that blue region as close to the Q's as possible?
Yes. So so since these points are at infinity, so this is just it seems a smaller region just because of I have the finiteness of the resolution that Mathematica can give me to construct this region. But you can imagine this T bullets to be very, very close to Q and Q prime. So we're actually covering a very huge portion of this cosmological, the cosmological part of the space. It's just that because of resolution, I cannot really, if I cut it too close, it's not really clear. Like we need to not include it, so it's more of the picture than the actual thing.
So I understand like the nature, so I have like an question. I understand like the nature of a characteristic in itself, but probably different from understanding, but somehow it seemed that you could take the purple line below as a limit towards the characteristic, the cosmological horizon. So more or less like technically what is the problem in taking that limit? Or?
So you can actually go very, very close. It just that it breaks down as R equal to RC. Because this is a no hypersurface, right? It's a no space like it. So you can go very, very close. And again, this is due to the picture because I can actually go very close, but then you will not distinguish the line in the picture. So if you want to see the collections of, so I have so I'm going too far. So yeah, so here, like there are some of them, but you can actually go further down in here, so very close, but never on the horizon. So it really breaks out. So you see the mathematical, like if you use that to exactly compute the exact position. So if you use the exact position of this, right? But you can.
Any other questions?
Your stability analysis sufficient, necessary, sufficient?
It's I mean it's the global result for the all regions. So its existence a uniqueness.
Sorry?
Its existence a uniqueness of the solution.
But in terms of stability, so you make an analysis. You get full stability.
You should get no linear stability, so the full stability.
Full
so,
non-linear stability.
Yeah, I mean for this portion, yes.
For
this the portion that we covered, yes.
Yeah, for the portion. Okay.
For the other portions, you can do so that compounds set. Then we'll drain the other part of square and then patch everything together.
So you mean this part?
You can have almost everything about it.
Yes, yes. So yeah.
That's the idea.
Yeah. So so because I mean we argue that since we can get close to RC, we can also include RC. We only need to include the asymptotic points. But then one can actually prove it because if you use the characteristic problem, then you can show that so the rectangular domain that you can define is contained in a hyperbola, then somehow you are covering one of the slices that we use. And so you get a similar state. You just, I mean, if you really want to be careful and then have actually initial data on the cosmological horizon, and think that you can really obtain this result in that case.
So first we have the results, but the perturbations cannot be very
Yes, small in the ball. Yeah, but you can take. Yeah, but since you can apply to all the episodes, you can take an episode that is slightly just an epsilon away from the one that you've done before, and you can do the same thing. So you can use all these hypersurfaces with constant R to do the same thing, and then you can patch all the results so that you get stability for everything.
That result captured, so it's a local result because you're close to square. That's just because you're on the conformal time, then you switch to physical time, then
yes,
it's a global result. Yeah. It's really a global result for
because then you take so the result that you translate back is the full result. So you translate only when everything is done, then you translate it back.
So it's global in time, but not in space, because you cannot go.
Yeah.
Actually, maybe if you go to the penultimate slide, there you can see it when you have the cuts of close. Yeah, so there you can see it, right? So actually, can you put the penultimate slide? So actually, his cutoff theorem goes from tau equals 0 to 5/2. So scribe is at tau equal 2, so they can go slightly beyond scribe.
Yeah, because the idea is that you can also use scribe because it's so if you stay here, you can also do the ball, and so you get like an epsilon more than epsilon in the cosmological, in the conformal setting.
And for the intersecting, you cannot have any other slice it outside and then do some matching of the intersector. This one probably difficult.
So you mean outside it?
So I mean, initial vector for the cubes,
and
then match with the other slice. So you can have
but then the problem comes from the equations that you use, because this Q and Q prime contains singularity of the conformal structure. So if you try to use the equation, then things breaks down Q and Q prime. It's not just that. Yes, I mean you can use them, but you need to try to rescale quantity that are singular there into quantity that are not anymore singular there, and then use a construction that allows you to control the evolutions and then include these asymptotic points. And this is what we're trying to do.
Any more questions? If not, let's thank our speaker again.
If you enjoyed the video, like and subscribe.